So, a very good morning to all of you. On behalf of the Civil Department of Anand Institute of Higher Technology, we want to welcome you all in the second day of this webinar, Corrosion Mechanisms in Concrete Structures. So, then the last day on the first part of the session, we saw about the corrosion mechanisms and how it initiates in the reinforced concrete system and some more details about it. And after that, the main two reasons, the two prime reasons of corrosion, one is that carbonation induced corrosion, which is happening due to the induction or due to the inducing of carbon dioxide gases into the concrete system, or carbon dioxide any form, and due to the chlorine induced corrosion. So today we will see the rest of the topics in the second day. So the rest of the topics includes that the chloride induced corrosion and the condition assessment of the embedded rivers. So here in the condition assessment, we will see that how to assess the condition of the reinforcement inside the concrete systems after getting corroded, and what are the processes and what is the need of this assessment. And we'll see them some details about the chloride induced corrosion as well. And at the last topic, we'll see about the some need of the preventive maintenance and some of the case studies across the session. So due to some technical errors, we changed the live session into recorded video session through YouTube links. There are some that limitation of participants also that we are having. So to overcome all those that problems, we came to conduct this whole webinar in the recorded session. So you can, if you have any queries and any doubts, you can mail us to the corresponding mail address, and you can also call us, you can WhatsApp us, which I'm going to share with you at the end of the session. So the first topic today we see about the some typical locations where we can see the chloride induced corrosion. So the corrosion may happen due to the prime reasons we told before itself, we discussed before itself. Two reasons are that chloride induced corrosion and carbonation induced corrosion. In the last session, we went through the details about the carbonation induced corrosion and the different that assessment process also to find the depth of the carbonations and the different parameters, the effects of different parameters such as humidity and the temperature, that affects the carbonation induced corrosion. So today we'll see about the details in chloride induced corrosion. Already we have mentioned that carbonation induced corrosion is one type of uniform corrosion, but in the case of chloride induced corrosions, it is a localized corrosion, or some pitting corrosion used to happen in this case of chloride induced corrosion. So we'll see in details about the things. So the first 2 3 slides I will show you that some typical locations or some that places where we can see, or some structures where we can see some chloride induced corrosion. So any structures which is constructed in sea water constructions, or which are very prone to marine environment, for these types of structures we can notice that severe chloride induced corrosion. So this is very common. The next type of that place or locations where we can see that chloride induced corrosion is some structures which are away from the marine environment but facing towards seaside, that is near to the coastal area. So if you can remember, in the last lecture we have discussed about the corrosion map of our country, that the whole coastal line. So in the coastal zone, there may be some chances to see these types of corrosions. This is due to the airborne chlorides and the soil rich in chlorine. So due to this, you can see some of the corrosions, which is totally based on chloride induced corrosions. You can see in the picture left side, and that shades they have given, some wrapping work is going on. This was due to the airborne chlorides. You can see also that this picture, the bottom middle picture, you can see that the construction they did, it was the soil, the fine aggregates they used, it was rich of that chlorine content. So they got some early corrosion. And one more thing, we have seen that in the coastal region, the water also sometimes used to be somewhat rich in chlorine. So you can test some salty test of water. You can, if you test water in some of the places in the coastal area, you can find that the taste of the water is somewhat salty. So if these types of water, suppose in when the that sewer pipes and all are going, you can refer the rightmost picture in the bottom, that you can see that in most of the buildings they will provide some gap in between the pipelines. But if you don't provide gaps, and if especially the pipes are made of plastic pipes or some PVC pipes, so when the water flows through the pipes, the pipes are suffering from some vibration force, or there may be some movement in the pipes. So if this place, or if the place is fully blocked, then the pipe will have some cracks, and the water will that comes out from this leakage, and it can create a corrosion. So to remove these types of problems, you can give some gap in between the pipelines. If it passes through any slab or in any element of the structure, it's better to give some gaps, so that the movement of the pipe or some the vibration of the pipe doesn't makes the pipe to crack, to have leakage. So these are of the some of the that cases where you can find chloride induced corrosion. And in some chemical plant also, which is rich in the localized chloride content, in that case also you can see some chloride induced corrosion. So the picture top left, you can see this is a storage of hydrochloric acid. So the entire environment, the local environment of this chemical plant is full and full of chloride ions. And you can see the cracks and the corrosions that happened. And even the that the vessel where they're storing the hydrochloric acid itself is getting corroded. So these are some of the locations which are these types of plants may be away from the coastal region, but you will see some chloride induced corrosions. So the picture bottom left, you can see this is actually a salt factory, so where they're manufacturing salts. So the local environment of that plant is quite rich in that chloride content, so that you can also see these types of chloride induced corrosion. Though the corrosion in this case, it looks like quite in uniform, but the full air of this that near this air, that salt factory is rich in chloride. So the corrosion is going on, and and most that prominently, this is a steel structure. You can see the truss types of structure, it is full and full made of steel. So that entire the structure is getting corroded. So these are some of the examples where you can see that. Then these are the examples where you can see the corrosion due to the usage of fine aggregates or sand, which was rich in chloride content. So then within some 5 to 6 years, you can see some corrosion if you use these types of fine aggregates in your construction. So these are some of the typical locations and very typical reasons where you can see the chloride content. So sorry, the chloride induced corrosion. So these are all the some of the examples. You can see that how the reinforcement and even the concrete is getting spalled out due to chloride induced corrosion. So now we'll see in detail about that chloride, the mechanism of the chloride induced corrosion. You can see already in the last lecture itself, I have told that it's a localized corrosion. So where in the concrete system, the entire concrete system, you won't find the concentration of chloride uniformly throughout the concrete system. If you talk about a mass concrete system, it is not possible to get a uniform chloride content everywhere in the concrete system. So I have given two arrows. One arrow is somewhat thinner and one arrow is somewhat thicker. So where the ingress of chloride content, or where the concentration of chloride is more, you will find that there is a pitting type of corrosion. In the right picture, you can see there is a pitting type of corrosion like this. So it's some holes or some that these types of deterioration will happen due to chloride induced corrosion. And it due to this, when the chloride reaches, multiple reaction happens in the concrete system, which we'll see in the next slide. So due to this, the passive film, I hope so these diagrams are quite familiar to you. So the passive film will break at some particular place, or at some point where the chloride concentration is more. So the passive layer will break due to high chloride content, and the corrosion will initiate at that point. And once the corrosion initiate, the chain of reaction mechanism will continue, and slowly it will transfer to the other parts of the reinforcing system also. And in the reaction itself, in the next slide, you will see the reaction itself. Once the chloride induced corrosion initiates in a concrete system, the chain continues and more chlorides used to form. So we'll see the mechanism here. So first, when the chloride in that ingresses in any of the concrete system, first it reacts when it reaches to the iron surface that or the reinforcing steel surface. It first reacts with the iron content, and it forms FeCl2. You can see here, this is the first step of the reactions. Fe2 plus 2Cl minus, it forming that FeCl2. It will first react with the iron. Okay, fine. Then this ferrous chloride FeCl2 will react with the moisture which is present in the concrete system, because we know that concrete is that moisture is always present in the concrete system. So this will react with the water or the moisture which is present in the concrete system to form hydrochloric acid and FeOH2. That FeOH2 is nothing but the rust, that product of the corrosion reaction. So this hydrochloric acid will get dissolves with the water, and again it will form 2H plus and 2Cl minus. So again you are getting that chloride content from the reaction itself. You are getting chloride content, and so again this chloride content will attack the that iron, and again the chain will continue. So so that's why chloride induced corrosion is very dangerous. Once it starts, it's quite that hard and quite difficult to make it stop. So there are some technologies to stop corrosion, but the initiation of chloride induced corrosion in any of the that RC concrete system is very dangerous. So the process is regenerating, and instead of spreading along the bar, corrosion continues at local anodes and deep pits are formed. So as I told that chloride induced corrosion is a localized corrosion. So what it will happen? So it will attack at a particular point of this bar, of the reinforcing bar, and then it will damage. I'll show you some of the examples where you can see that that nothing is left in the reinforcing bar. And the full that load carrying path due to this reinforcing steel will get damaged if these types of corrosion happens. So this is the corrosion mechanism due to chloride induced in induction in a concrete system. You can the next slide we'll see about some pitting corrosion examples in pre-stressing strands and the deformed bars. So the that for you can see that in the pre-stressing strand in the top picture, I have already marked some red markings, so that there are some corrosions in that particular zones. So you can easily see that the whole strand is not getting corroded. Some localized corrosion is happening due to chloride attack. And now if you take some cross sections, let me annotate you. Just hold a bit, I am annotating. So if you take a cross section here, and if you take a cross section here, and if you take a cross section here, the different cross sections will be different, and the places at which the pitting has been formed due to this corrosion, in that particular place the stress experienced by the strands at that particular place will be high, because the area of cross section is less. As we all know that stress is inversely proportional to the area of the cross section. So at that time, so these particular points where the pit will be there. In the case of deformed bars also, you can see down in the bottom picture. In the case of deformed bars also, you can see there are some pitting types of corrosions in some of the places, but here in this place there is no corrosion. So what is the main that drawbacks in this chloride induced corrosion is there may be some sudden breakage of the bars, or there may be some sudden breakage in the pre-stressing stress, as because in some of the points the stress induced or the stress experienced by those particular points where there is pitting, it will be more. Anytime when the load due to the continuous loading, there may be some breakage in the strands or the bars. So it is quite that devastating as compared to the carbonation induced corrosion. So now these types of corrosions, either chlorine induced corrosions or carbonation induced corrosions, may be that we can control by using bipolar corrosion inhibiting admixtures. So already we have used these terms in the previous session also, the corrosion inhibitors. So we can use corrosion inhibitors like as admixtures to with at the time of mixing concrete itself. So it comes under the that experience or under the practice of corrosion prevention, not corrosion protection. I explained these two terms earlier. So if you want to prevent your structure from the beginning itself, you can induce some corrosion inhibitors or some admixtures. There are n number of admixtures available to that inhibiting corrosions in the market. So previously we had that monopolar type of inhibitors, where the inhibitors used to protect the steel from the anodic reaction. But now we have that bipolar type of inhibitors, which helps to resist both anodic and cathodic reactions in a concrete in a corrosion cell. So we'll see some of the parameters that how the use of corrosion inhibitors may change some of the parameters in a concrete system. So we cannot use inhibitors according to our wish and all. So, and there are some that bad effects also. So we'll see some of the parameters, how the corrosion inhibitors are changing those parameters in concrete system. So what happens when you that you can see that the green layer is, you know about the green layer around the reinforcing bar. Now this is nothing but the passive film. So due to this, when you that add corrosion inhibitors, it protects the passive film and it makes the passive film somewhat thicker and strong. So by which it resists the and that entry of chlorides as well as the entry of carbon dioxide, and it helps the that reinforcing system to get preserved. So now we'll see some of the that transport properties, not transport properties, that some parameters based on the water cement ratio of the concrete system. So these are the examples or some tests done in IIT Madras, in the lab of IIT Madras. So what they have seen that some at the some control structure at the 0% addition of inhibitors, the chloride threshold of the concrete system was found as zero point 0.3. So now what is chloride threshold? So it is the that time, or the initiation time of chloride induced corrosion. So chloride threshold is about the time, after how much time you can make the concrete structure without any corrosion. You can keep the concrete structure without any chloride induced corrosion. So like this chloride threshold, we are having carbonation threshold as well. So it has been seen that by using that without using any inhibitor, the chloride threshold was zero point 0.3. In the case of water cement ratio, zero point 0.4 I am talking about. And the percentage of inhibitors that they have mixed is the weight of the cement. The percentage of inhibitors was calculated by the weight of the cement. So now when they have used 0.5% of inhibitors by the weight of cement, it has been seen that the chloride threshold has been increased by to 0.4. So it works well. And when they again added plus more 0.5 percentage, that is 1 percentage of that inhibitor, the chloride threshold has been increased to zero point 0.5. So there is you can see that a significant increase in the chloride threshold when they have did this test with by maintaining a water cement ratio of zero point 0.4. But now in the case of water cement ratio 0.6, there is no that much significant that increment in the chloride threshold has been noticed. So the we can conclude from this that graph that usage of corrosion inhibitors with higher water cement ratio will not give you a good result. The corrosion inhibitors works good at low water cement ratio. If the water cement ratio is high, the corrosion inhibitors are not working properly to increase the chloride threshold. So we have to see about the without watching that, without experiencing or without testing the different parameters, we cannot use that inhibitors. So otherwise at the end we will come up with the conclusion that the inhibitor is not working or the technology is not working. So the appropriate use of corrosion inhibitors can increase the corrosion initiation time by 2 to 3 times. So if we use the recommended dose RD or the appropriate use of corrosion inhibitors, we can that increase the corrosion initiation time by 2 to 3 times. So that like this we have to go for different parameters. We'll see the next parameters in the next slide. So this parameter is of the compressive strength, because we know that concrete is we are using concrete system because the concrete is very good in compression strength. So so that compression strength of any concrete mix is quite important. So now in this that graph we'll see that how the dosage of the corrosion inhibitors may affect the compressive strength of the concrete system. So without using any inhibitor, the first graph, no inhibitor, I am annotating for you. So in this case, no, without using any that inhibitor, without using zero inhibitor, we got the that compressive strength near to 37 MPa, 37 megapascal. But when we use recommended dose, then also we got the same type of compressive strength. You can see the that in the graph itself, you can see we got the almost same compressive strength. But we have, when we have used the that corrosion inhibitors by -20% and -40%, there is a decrement in the compressive strength. There is a gradual decrement in the compressive strength. And even when we have used that more than the recommended dose, plus 20 percentage and plus 40 percentage, then also we have seen that there is a gradual drop in the compressive strength. So addition of corrosion inhibitors, either less or more than the recommended dosage, may give a negative impact on the compressive strength of a concrete system. So we have to adopt a proper dosage to maintain the compressive strength of the concrete system, because compressive strength is quite important property for any of the RC system, RC concrete system. So now we'll see some other parameters. So now how the corrosion inhibitors may that affect the transport properties in a concrete system. Transport properties is nothing but the how the deleterious elements or the moistures or different types of elements are getting ingress into the concrete system. This property is known as transport properties. It is directly linked with the permeability of the concrete system. So now we'll see that when we have in the case of we have taken actually this test was done in the laboratory of IIT Madras. So when they have used some three types of corrosion inhibitors for doing some test. So in the case of corrosion that inhibitor A, when they have they studied the water softivity index. They studied the water softivity index. This is also transport property. So it is that how, what is the rate by which water will enter into the concrete system, water will ingress into the concrete system. So this is coming under one of the transport properties. So they have studied the water softivity index in different concrete mix by using these three different inhibitors, and they found that when they have used that recommended dose, in the case of control without using any inhibitor, the water softivity index was near that 14 or that near to 15. But when they have used recommended dose, then they got the water softivity index as 27, 25 plus. So that by using the recommended dose itself, here you can see in this case, and the water softivity index has been increased. In the case of inhibitor B, same here also in this case, without using any that inhibitors, the water softivity index was approximately about 6. But after using the recommended dose, the water softivity index is has been increased to 15. So in the case of inhibitor C, you can see that by that after using the recommended dose and before using the recommended dose, the water softivity index is quite similar. And you can see that they have mentioned about the that limit of by who up to how that up to how we can see that the performance is excellent, good, and poor. If the water softivity index is within 5, within the range, within the range of 5, or if it is below 6, then we can say that the concrete is excellent in the case of water softivity index. And if the range is within that 6 to 10, we can say that it is a good in the case of for water softivity index. But if it is more than 10, in between 10 to 15, it is poor, and if it is more than 15 means it's very poor. So you can see that all the inhibitors are not acting properly in all type of concrete mix. So before adopting any type of corrosion inhibitors, you have to go through this test. Otherwise, after implementation of all those things, you will find some devastating effect, and you will conclude that the technology was bad, or either the material was not good. You will blame, the blaming game will happen in between the contractors and the designers and all. So before adopting any type of admixtures, so here we are talking about the corrosion inhibitor. But in case of any types of admixtures, or if you want to change your conventional mix by adding something, so it's quite important to go for the fundamental tests before implementing these into the construction. So adding of corrosion inhibitors sometimes affects the transport properties of concrete. So in this case, we have seen that the use of recommended dose of inhibitors increases the water solubility index of the concrete, which means moisture will ingress faster to the concrete. So if the water solubility index is more, so that moisture will ingress into the concrete system at a very high rate. So dosage of inhibitors influence the durability of any concrete system. So whenever we are going to choose any type of inhibitor, we have to choose this very carefully. So now we'll see some of the structural cracks. So hope so this diagram is very quite familiar to you. So in this you can see there are two types of supports they have shown. One is that simply support and one is continuous support. When we applied load, you can see different types of cracks in any type of flexural members. Here you can see this. Let me annotate for you again. So here you can see these that flexural cracks, and these are all the that shear cracks, and these are all the cracks that are due to negative bending moment. In the continuous support, you will find negative bending moment at the top. Due to this main negative bending moment, you will see a tension zone in the top of the member. So the red line indicates the tension zone, how the tension zone differs in such types of cases. So now why I am showing you these cracks in these corrosion mechanisms, because now you see that the deep blue color straight lines, that deep blue color straight lines, let me show you again these lines, and here this line. So suppose consider this as the that reinforcing steels or embedded bars. So if the bars are coming in between these cracks, so this bar will be very prone to different types of deleterious agents. So automatically the chloride or the carbon dioxide will enter through these cracks, and it will initiate the corrosion in between the that reinforcing steels. So it is quite important to maintain the structures and to prevent the structures from these different types of cracks, because not only the agents will that ingress the concrete system through the that pores what the concrete system is having. The main reason of that ingressing the deleterious agents is cracks. The easy way to initiate the corrosion is due to the cracks, because from these cracks only different types of agents are uh, entering into the concrete surface. So we'll see some of the examples. So here you can see some of the examples in the left side. I marked some of the cracks in the black color. These are very thin cracks, and these cracks was formed due to the early removal of the scaffoldings or the frameworks before the concrete gained is that sustainable strength. Before gaining itself, they have removed the frameworks. So for that purpose, there is a elastic shortening, and the concrete tries to settle down. It was not fully in the elastic stage. Before attaining the elastic stage itself, they have removed the that framework, so it was in a partial plastic stage. Thus for that particular reason they got some cracks. Now you imagine the red line as a reinforcing bar. So if you imagine that there will be some reinforcing bars, since it is a flexural member in the tension zone, obviously there will be some tension, that tension reinforcement. So due to these cracks, the that different types of deleterious agents will enter into the that concrete systems and to initiates the corrosion. In the right hand side also you can see there are some there's cracks and formations of scales. I have marked here the formations of scales. You can see white color scales formation. This may be due to two reasons. According to me, it may be due to the early removal of the framework, or it may be due to the shrinkage of the concrete. So what the thing or what the message I want to give, that you can see the moisture is coming out from the concrete. So obviously there is a passage, there is a crack in between. There is a crack in the sense there is a passage through which the moisture is coming out and accumulating on the surface of the concrete surface, forming scales. Now you imagine that blue color lines as reinforcing bars. So obviously these bars will very soon these bars will suffer from different types of corrosion. So you can, this is that example, that sinkage cracks in roof due to poor mixed design. It may be due to poor mixed design, or it may be due to poor curing practices, or it may be due to the early removal of the that scaffolding. So the cracks are very dangerous in any types of concrete structures. Why I am showing you all those things in the I'll show you some of the examples and some that how the owners of the building and the engineers who are associated with this building are neglecting different types of cracks and all. I'll show you. So this is very dangerous. So I got a lot of queries like that, how the old structures are still now standing erect and all. Even I hope so in the last session also we have discussed on this topic. And nowadays very new structures within some 5 years, within some 10 years, we used to get some corrosion. So as I told that if any of the construction site they use some fine aggregate which is rich in chloride content, then obviously within some 6 years you will see some corrosion. And some of the practices like these in these slides what I'm showing you now, these types of practices may also maybe the some of the reasons of corrosion in induction that induce of corrosion in any concrete system. So now I will show you that how the cracks may that initiates different types of corrosion. It's a case study, and we have seen that different types of deleterious elements are how it enters through the crack and how it that affects the reinforcing bar. So in this case, it has been we studied the that carbonation induced corrosion. So through this crack, when we have sprayed that phenolphthalein indicator, it has been seen that the near the places of the cracks, you can see it is fully acidic due to this presence of carbonic acid. What we have seen in the last session. So the places here you can see this place. I am going to annotate you. So this place is full and full getting acidic. So through these cracks, you can see that slowly it will ingress, it will increase into the concrete system deeper, and it will start corroding the entire rebar system. So in this case is only for the carbon dioxide, but not only carbon dioxide, that chlorides, oxygen, and moisture, any types of deleterious agents may ingress through the concrete system easily in the through the cracks. So it's like a passage. We are creating a passage for the agents to enter into the concrete system. So if you see a lot of the corrosion case study, you will never see that without cracks or without forming any cracks there are some that initiation of corrosion. If the corrosion rate is fast, it is obvious that there may be some cracks formed before itself, through which the agents enters the concrete system in a faster rate. If you see the permeability, so if some of the cases it may be okay if the that environment of near the concrete system is quite prone to corrosion, means at that time it's okay. But in normal residential buildings and in normal construction cases, the agents are going through the concrete or ingressing the concrete system through these types of cracks only. So it is quite important to look after the cracks. So what will happen ultimately? So we will find a local corrosion here, localized corrosion here. Since this is also as it is for the reason is for carbonation, but still you will find some localized corrosion. So there may be a problem to detect the root cause also in some of the cases. So at that time you have to go through all these tests to find out the root cause. So we'll see some of the case studies in the upcoming slides. So now, according to AISCI 224R, there are some that they have mentioned some tolerable crack widths. So you can see these times these of that for different conditions, different service conditions, what are the tolerable crack widths. So you can see this data. So on beside of this, I want to say you in the right side picture, you can see that the cracks and the process by which the agents are getting inside the concrete system, and the cover depth plays a vital role in such of the cases. So if you have a less cover depth, or if your that effective cover or the clear cover is comparatively less, then easily the cracks may touch the reinforcing system. So to make your concrete somewhat more permeable, somewhat more impermeable, so you can ensure an adequate cover depth. If the cover depth is more, the depth of the cover is more, and then you can see that example what I'm showing you in the right side, and the picture down. Due to this adequate cover depth, the crack doesn't reach the concrete, the steel surface. But if the cover depth is less, you may have some problem like this. So that adaptation of adequate cover depth is quite mandatory to reduce the that ingress of cracks into the towards the steel surface. So now I'll show you about the what is the need of condition assessment and the various tests. So this is a that case study that you can see there is in the picture left side picture. You can see there is no visible corrosion marks on the concrete surface. So generally what happens when that any of the reinforcing steel bars are getting corroded, due to corrosion there is a significant volume increment, and this volume increment gives a pressure to the concrete surrounding this bar, and the concrete surface starts cracking, followed by that's falling out. But in this case you cannot see any that stains of corrosion on the concrete surface, no markings and not even cracks also. But when the concrete has been removed for assessment purpose, it has been seen that there is some significant corrosion inside the concrete system, inside this concrete RC system. And in the picture in the right side, that you can see that magnified view, you can see that almost nothing is there in the concrete this part. So I can that's why I told you that chloride induced corrosion is quite dangerous. That so at any time this may break, and there may be some detachment of the reinforcing steel, and it may create a problem in the load transfer path. So this is a case. So from this that slide, the message I want to give you is that, so what is the need of non-destructive test for the assessment of the reinforcing bars and also the concrete system. So in this case you have seen that if we don't do any regular condition assessment or different types of non-destructive tests, there may be some hidden corrosion, and which may create a problem in the later stage. So you can see here in the picture left side, nothing was there, no cracks, and not even these stains also. So in that time you so what is the need that if you don't do the non-destructive test, and if you assume that the concrete surface is good and it's performing well, so it will be a wrong judgment. So we should have, if even after the construction process regularly, we should have some we should have some monitoring management team or corrosion management team in any of the construction companies or in any of the construction association, those who will take care of all those things. So we cannot leave a structure without assessing it for a long time. It will be a wrong judgment if you do like this. So here I am again. Telling you the mechanisms how it happens in the case of deformed bars. So corrosion in a typical deformed bar. So this is somewhat similar as in any types of steel. Last session also we have discussed about it. So what happens? So when the corrosion products that rust gets accumulated on the that steel surface, the volume increases and it gives some early expensive stresses. So why I have used that word early here, because in the case of pre-stressing strands and in the case of deformed bars, the scenario is somewhat different. In the case of pre-stressing bars, so this is a separate topic which we are planning to come out in the next webinar. So I am going to give you a light touch here, small discussions regarding what happens at the time of pre-stressing strands. So you will have some multiple strands which will make a cable. So if then when the strands are binded together, at the time you will find some spaces in between the strands. So when the corrosion initiates, first the corrosion products will get accumulated in that particular spaces inside the strands, when the space will get filled, then only the products will come out and will get start accumulating on the outer surface, which will give the expansive stress. So that this, in the case of pre-stressing strands, some hidden corrosion may happen. We may not see the expansive stress what we used to see generally in the case of that deformed bars. But in the case of pre-stressing bars, we may not see the corrosion strains or some cracks due to the corrosion in the concrete system, because the volume that or the space what is available in between the strands, we'll discuss in the upcoming webinars in discuss in detail about this. So first the corrosion products will accumulate on that particular spaces in between the strands. After that only it will come out on the outer surface and it will exerts pressure. But in the case of deformed bars, the rust, that there is no other that hidden place for the accumulation of the rust products or the corrosion products. So from the beginning itself it will start giving the expansive stress towards the concrete, which is very near to the bar. So this stress will lead to cracking, and the manifestation of corrosion products will be there, and we'll see ultimately some cracks and stains of corrosion on the concrete surface. But in the case of pre-stressing strands, there will be some hidden corrosion, and which will result in the delayed formation of the corrosion strains in the concrete surface. So in the case of, so we cannot judge a normal conventional RC building with a pre-stressed concrete building. If you see that some stains in the case of a normal RC building, you may conclude that, or you may judge that the corrosion might have started very shortly. But in the case of pre-stressing structure or pre-stressed concrete structures, if you see corrosion stains on the concrete surface, it is quite dangerous. So you have to immediately you have to judge that uh, the corrosion has started long before itself. So this mechanism I will show you in the future webinar, where we'll discuss about in detail about the pre-stressing corrosion in pre-stressing system or pre-stressed concrete systems. So now there are some examples. So you can see that left side picture, that how the concrete surface used to get damaged and how the concretes are getting spoiled due to corrosion. So this is an example of salt attack. So the rust stain is visible, and which is a proof that corrosion is going on and we have to do some repair work. So, but in the case of pre-stressing concrete, if you see such types of stains, what you can see it now in the left side. If you see such types of stains, that there may be a huge damage in the that pre-stressing strands, because the corrosion has been started long before. So here in the right side, you can see how the concrete can spoil due to this that volumetric pressure that exert the pressures which is exerting by the that corrosion products. Already we have discussed in the last webinar that there may be some 6 to 8% of volume increment of the rivers for corrosion. You can see how significantly the corrosion that the concrete has been came that the full cover concrete. So in the case of corrosion, you can always see that the cover concretes are getting affected, because the strength of the cover concrete is somewhat less. They are very weak in tension. So due to this pressure, the cover concretes are getting first the cover concretes are getting affected. Now in this case, this is also a case study where you can see that the left side picture, they have provided some coatings. It actually, this is a floor of car parking. So they have provided some coatings and all that some, and due to some poor drainage systems, there is some leakage in the deck joints. And the due to this corrosion, again the without identifying the root cause, they just did some patchwork, and they provided some coatings. But it has been seen that there is some leakage in between the deck joints. And again the same problem has been that came out, and you can see that how significantly the coating also has been getting delaminated. And you can see that blue circles there. You can see that pitting types of the damage has been occurred. You can see that red markings, they actually, this is nothing but the joints So some that leakage is there in between the deck joints. They didn't that followed this one earlier, or they might have neglected this one, but later it has been seen that the capital that they have used for this repair work was full and full of loss. It actually didn't work. They did some repair work, but it doesn't last for long because they didn't find out the root cause. So finding out the root cause is quite important. In the case of that right side picture, actually this is a composite type of column. They have used some that steel sections of I sections. It's composite column. So here also you can see that how the concrete is falling out due to this corrosion pressure. That same type of thing what we have seen in the case of that beam in the earlier slide. You can see that falling of concrete due to this 6 to 8% volume increment. So finding out the root cause is quite important, and these are some of the examples how you can see the cracks and spalling of concrete due to corrosion. So now in this case, you can see this is also an example where due to carbonation induced corrosion, that how much damage it can do in a that steel surface inside the concrete. So sometimes we see that there may be some cracks, there may be some stains, and it's very common in any types of structure. It may happen, but if you see that, know how that this bar I am showing you, if you don't take these things seriously, suppose this particular place, you can see that this is a uniform types of corrosion. Entire the length you can see there is a corrosion. So and this place has been affected much more. So if you left this structure in such a way, so it may create a problem, and the user of these types of structures may suffer from different problems in future. So it's quite important to take care of all those things. So over time, carbon dioxide gas from the atmosphere can acidify the concrete. We know about the mechanism of carbonation induced corrosion. So it can acidify the entire concrete system surrounding the river, which will break the passive film and induce corrosion. So these are some of the examples. You can see how that severely the reinforcing steels may get damaged due to corrosion. And and by knowingly by we have the idea that what can happen in some of the system, but still we are neglecting. So the message from this slide is to show you that what happens inside the concrete system, what corrosion happens. So we should not neglect if we see any cracks in a building or any corrosion stains in a building. I'll show you some of the examples what happened. So now this is also an example in that swimming pool of Woodhouse Leisure in 2013, the case study, and the assessment, the condition assessment was done by the Concrete Preservation Technologies (CPT). And it has been seen that they did some lot of that repair work, by patching work, and that removal of the concrete and all. But the it has been seen that significantly the same types of again and again the same types of that things are happening. So that special team, they came and they investigated this particular problem. You can see the spalling of concrete and the reinforcing bars are getting corroded. I am annotating for you. So here you can see a significant corrosion stains, and that one also you can see. You can see that how the corrosion, that bars are getting corroded here, and how the concretes are spalling out. So in this case, they did some assessment, they did couple of tests, and they find out some of the things we'll see now. So the age of the structure was 40 years, and it has been seen that the inner wall of the swimming pool was suffering from concrete spalling and delamination of the concrete due to corrosion. The corrosion is there, so it is very prominently we can see that it is prominent that corrosion is there. But what is the reason of corrosion was the problem here. So they did some condition assessment, and a series of tests was done. They find out the depth of carbonation. They find out that chlorine profiling of the that system. They did half cell potential test, and they find out that this particular that concrete system is suffering from both carbonation and chlorination. So they that adopt some Dugard hybrid anodic system to stop the corrosion. So this is a protecting type of technology or protecting type of repair work they did. So thus testing these types of this testing data help them to complete their condition assessment nicely, and it helped them also to find out the root cause. So without finding root cause, if suppose what they did earlier, they that removed the concrete surface, they did some patching work, they removed the that embedded steel, some of the steel which was getting too much corroded, so it won't stop the game inside the concrete system. So they should find out the reason why these types of corrosions is happening, and why the delamination is happening, or what is the reason behind the distress of the structure. So these types of tests, the series of tests help them to find out the root cause. So later they have introduced some anodic system. So we'll see the technology later, that in details about what are the different types of technologies. Most prominently, or most that not typically adopted technology is that anodic system. What happens actually in the concrete corrosion cell, we have seen that the anodic part of the reinforcing steel is getting corroded, or is getting deteriorated. So they introduce some artificial anode, which will that corrode instead of the steel bar. So there is a technology what we have discussed in the last webinar, and we are planning to come up with the new webinar where we discuss about some that continuous that new technologies, how to arrest corrosion and how to stop corrosion in the concrete system. So this is actually case study. I showed you that, and this message I want to give from this case study is that condition assessment is very very important. So if you don't do condition assessment, there may be a problem in the structure. There may be some hidden corrosion, what we have seen couple of slides earlier. And for determining the root cause of distress, that condition assessment and the different types of tests are quite important. So now, if you leave the structure like this, so without doing some that monitoring of the structure, or without doing some condition assessment, if you leave the structure like this, ultimately you will end up by getting structure like such case, like this way, what you can see in the screen now. So severe corrosion and severe that concrete has been delaminated, so it's a severe damage. So typically we used to say that if there is a loss of 10 percentage cross sectional area in the reinforcing bar or in the embedded bar, we have to replace the bar, or we have to embed some new bar. So now the challenge here is how to determine the 10% loss of the bar. So in the document, you can mention that there is some 10% loss of the bar. You can judge by your own way. But if you want to really find out the 10% cross section loss across the length of the bar is quite very difficult. So this is a challenge we are used to that face for the every time cases, and the engineers and the that contractors are used to face a problem in this particular place. How to understand that there is a 10% loss in the cross section? I'm not telling the weight. And if you want to find out the 10% weight loss, then you have to extract the bar. Ultimately you have to damage the bar. So without damaging the structure, or without doing any destructive test, it's quite difficult to find out the 10% loss of cross sectional area. And even after that taking out the sample from the site itself, it is quite difficult to find out the 10% loss. So now, how to measure the cross-sectional loss? So some of the experts from IIT Madras, they did some experiments and some of the tests, and due to, on research basis, and still they didn't able to come up that with any type of that convenient method to find out the 10% loss. So we'll see some of the tries what they did to find out these types of 10% loss. So now, actually, why it is a problem, and these are some of the reasons. You can see that in the entire throughout the length of the bar, the deterioration will not be uniform in each and every cross sectional, if you consider. So you can see some of the pictures how it may differ place to place. So for that particular purpose only, it is a problem to find out 10% loss across the length of the cross section. And even due to this deformation in a corroded bar, it is quite important also to determine the stress strain behavior across the length of the bar, because in different place the behavior will be different. So if and especially if you talk about the stress strain measurements, so it's quite difficult to get a uniform stress strain measurements across the length of the bar. I'll show some one example here. In this case, this is the example of, this is a bar which is that corroded bar which has been extracted from site. So now if you fix some three extensometer, E1, E2 and E3 in three different places. So E1 will take the extension in between these 2 points, and E2 will take the extension in between these 2 points, and E3 will take in between these 2 points. So now when you will give some tensile load, so it is quite obvious that you will find three different types of data from three different that places. So what we can do is we can take average and we can say that this is the behavior or this is the measurement. So this is the actually problem what happens in the case of that deformed bus, or the deformed bus, sorry, not deformed bus, that corroded bus. So why it happens? Because, yeah, let's come back to the previous slide. Suppose in this case, if you see that, let me annotate. So in this case, the cross section is quite less as compared to this place. So here the stress will not be uniform. So if you see that in this place, the stress experienced in that particular place will be more as compared to this particular place. So like that, due to this deformation, the strain measurement in the different place will also be different. So enter that graph, that enter graph from each and every place. Suppose from that extensometer, from that gauge, if you take any data and if you plot a curve, and from this E2, if you take some data and plot a curve, and as well as for the same for E3, you will get some different graphs. But the different graphs will show you different properties or different behaviors, but the test has been done in a particular bar. So this is the problem we used to face in the case of that corroded bars. It's quite difficult to say that what is happening in each and every point of the bar if you speak about the entire length. So if you are going to determine the stress strain measurements, the data that you will obtain will be different at different points of the rebar across its length. So this is also a reason why we cannot able to find out. So this is a reason for the stress strain behavior. Similarly, we'll see some of the effects why it is quite difficult to find out the cross section loss. So now in IIT Madras, they did some test, the vernier caliper, liquid displacement method, and wax molding. So in the liquid displacement method, they tried to find out the cross section loss by how much amount of liquid has been displaced. They tried different types of solutions, but it didn't work. You cannot find out that about, you can see that how much volume of water has been or the water or liquid has been displaced, but it's quite difficult to say that how much is the cross section loss. Now you, if you come in the case of that vernier calipers, so you may say that the diameter is circular, but in different place you will find different types of diameter, and you can, so how the diameter is changing, that picture I'll show you in the next slide. You will come to know that how wrong the data will be if you take the that measurements by using vernier calipers. After that, they come up with a new idea by wax molding and all, in which they mold, they try to get out a picture of the deformed bars, how the area or the surface of the bars are getting damaged, but it also didn't work nicely. And that drawbacks are at the time of demolding these specimens and all, there may be some breakage in the wax mold, and so it also won't give you the that perfect that idea about the cross section loss. So now for the research purpose, they did some rapid prototyping type of that technology, and the data they have used. So they have taken some 13 specimens of corroded bars from the same structure, and the that white mark you can see they mentioned the cross section with the basis of this white mark. You can see the white mark. So in different places the cross section is different. So now you can see in in the top they have mentioned about the cross section, how it looks like. So you can see here. Wait, I'm sure I'm annotating for you. So here you can see that not a single cross section is circular, all are of different shapes. So and this particular shape, this particular shape is based on this area, this particular cross section. So like that they have mentioned that cross sections, they have that point out that how the cross section is changing lengthwise. So if you use a vernier caliper to take a diameter, see that how wrong it would be. So for that, up to now, there is no technology which can give you a perfect idea of this. So in future, there may be some technology which can give us any convenient method by which we can that say that how much may be the cross section loss. But now that this rapid prototyping system or technology seems somewhat that convenient. So, but the challenge here is we have to extract the bar from the site, and we have to do some laboratory test. We have to bring the specimen into the lab for doing this test. We cannot do this assessment on site. So this is the challenge here, and we have to do use some that sophisticated types of that instruments for getting these types of measurements. So so now, so it's quite difficult to say that how much is the cross section loss. So what we have to do is we have to utilize our engineering judgment before replacing or that before introducing any new reinforcing system in any corrosion repair work. So now the some of the techniques I'm going to say you very lightly and very briefly. We're going to discuss about some of the techniques and tests what we can use for different types of assessment in that corroded steel bars or that like that, or in any that corroded RC concrete system. So rapid prototyping method what we have discussed earlier is one of the technology. And that digital image correlation technique, this is also somewhat the technique that some technique we can use it uh, for determining the that different behaviors in corroded rebars. So in these techniques what we used to do is we are going to analyze the bar by do some that pixel by pixel judgment. So what we'll do is we'll have some that black paint into the on the surface of the bar. After doing the black paint, we can sprinkle some white color paint. We can sprinkle and we can uh, place the specimen into a high resolution camera, and we can do the test tensile stress. So we can see if we take some multiple images, and we can see that how the pixel is changing and how the pixel is moving due to the action of the load. So like that also we can do some we can judge what is happening point on different points in a corroded steel bar. In the next test we can do is half shell potential test. This is a like some based on some potential. If more the potential in this case, in this case of test, the more the negative the potential will be, there may be some more chance of corrosion. So half cell potential test can be done by different ways. We'll see in detail about it in the next webinar. So half cell potential is a very quite important test for determining that corrosion, or it can give us that the idea that about it's like mapping type of thing, that without damaging the concrete itself you can do it. So only what you have to do is you have to drill a hole into the concrete system, and you can it's like that cell type of thing, that electrical circuit for potential measurement. You will measure the potential in between the concrete and the steel, and more negative the potential, there may be more chance of corrosion. So based on this you can make a contour map across the that concrete surface, and you can say that which place may suffer from corrosion, or which place are more that dangerous for corrosion. And the next test is ASTM G109 test, which is using for determining chloride threshold. So one thing I want to mention for this test actually is not that introduced for determining chloride threshold, but many of the users are using this test for determining chloride threshold, and based on the that initiation time of the corrosion. So we'll see that these things also in the upcoming webinars. And the next test is that linear polarization resistant test. And so this is the one that useful test what by which we can find out the corrosion rate. Suppose a structure is suffering from corrosion, we will already know that the structure is suffering from corrosion. To know about the rate of corrosion, we can use this test, and this test is quite useful. So you can find the instantaneous corrosion rate in this case of test. And then the last one here is the guard ring technique. So this technique we can use both on site and as well as in laboratory as well for measuring the corrosion rate. So these are some of the that assessment test we can conduct to determine the different types of corrosion mechanisms and corrosion that picture what is happening inside the concrete system. So now that need for that preventive maintenance, you can see that that how that some of the pictures I'm showing you, that this is some unwanted things that what we used to tolerate. So in the picture in the left side, you can see there is a chimney, and in the top there is some plant. So what is the engineer who is that the in charge of these types of buildings and structures, who will be responsible for this kind of activities? So already we know that due to this biofouling and that formation of these types of plants, their roots will ingress in the concrete system, and it will exert pressure, and it will form cracks, and it will damage the entire structure. So that preventive maintenance is quite important, and there is no need of growing tree in the top of a chimney, I think so. And here also there is no need of these things. So who will be responsible for these types of things? You can see a lot of structures, a lot of important structures as well across your area. You will find these types of things happening, and we are neglecting all those things. So that we have to take these things seriously, and the in charge of the building, or the engineer who is responsible for this building, or the owner should take these things seriously, and they should take necessary steps for saving these structures. So precautionary maintenance approach is quite essential, and it can also help to save the amount for a long-term basis. So there is no need of allowing these plants or trees to grow inside on a concrete structure. So it may happen in some of the cases, then and there is we have to demolish. Otherwise, that if we don't do this maintenance work, we have to end up with some devastating effect. We have to end up with some different types of the distressing in concrete systems, and again we have to go for repair work. So the scenario and this mechanism is not good actually. So what is the need? We'll see in some of the case studies upcoming slides in the upcoming slides. So this is a case study in a building in my local area. So this is actually water leakage from bathroom. So due to capillary suction, water from the other side of the bathroom, or from the inside of the bathroom, is transporting to the other side of the wall, and you can see they are getting some patches, white marks in the that surface. You can see here. I'm going to annotate for you again. You can see some. These are some of the white patches, some line types of white patches they are getting, and the paintings they are coming out. So they are do some multiple type of regular painting, and they are see that how the painting it was before, and within some 8 months, it has been transferred like this. Within some 8 months to 1 year, it has been transferred like this. So again and again they are doing some this painting work, and they are coming up with a conclusion that what is happening, the painting may not be good, or there may be some problem with the laborers, those who are doing work like that. So later, for some that inspection purpose, we took this thing, you can see how damage, what type of that you can see near the bathroom door itself. Fully the place has been damaged. The concrete, the painting is fully coming out, and the surface of the concrete is also getting that full, that a lot of scales are forming. So now what we have did, that we went inside the bathroom and we have seen that the sealants, that the tiles they have used, they are not cleaning the tiles properly. They are not maintaining the tiles properly, and due to this, the sealant that what they have used, that sealant, this sealant in between the two tiles, the sealants are getting delaminated, and through this that gaps, water and moisture is getting ingress into the concrete system. You can see that full and full it is wet condition, and lot of fungus and different types of that biofouling has already has been happened inside the concrete system. So the user of this building is not taking these things seriously, and for aesthetic purpose they are painting the outer surface of the wall, and they're not able to keep the painting safe for a long time. So the reason here is due to this the delimitation of the sealant. The quality of the sealant was also not good. What they have used, due to this sealant, the breakage in the sealant, the water and the moisture is getting accumulated into the concrete surface, and slowly it is transporting towards the other end of the concrete, other end of the wall. And when we have removed some of these tiles, we have seen that there are some accumulation of earthworms also inside the tiles. So thus now you see that how much maybe the gap in between the two tiles, so that the earthworms are easily getting inside of the that tiles. So this is some of the negligency what that owner and the users they did, and now they faced a lot of problems. They wasted a lot of capital by painting once again and again like this. So due to capillary suction, water from the other side of the wall is transporting to this side, creating a damping in the wall, and later the root cause was determined. So so you have to examine the structure very nicely what is happening. So simply if you do the repair work, some patching and painting, it will not end up your problem. It will not end the problem. The problem here was something different. So we have removed the tiles, and we did some good tiling work and good sealing work. And later it has been seen that no such delamination happened in future after that. So here actually this is a example of my own apartment where I am staying. This is actually the left side picture is the inner side of the right side picture. I'm going to annotate you. This left side picture here, this is the inner side of this area, this particular area. Okay. So if you see the structure from this angle, you will see this particular side. So now what is happening due to some rainy season or when rain happens. So these pictures I took very recent pictures only. So I was preparing that module for you people. So I thought that to give you some example of negligency of these types. So how people neglect these types of things. So I got my own apartment as a good example to share with you. So you can see here that this is a place actually. This is the water tank, and this is a place where this place has been given to just for that. For inspection purpose only, but there is no proper drainage they have given in this particular place. I am showing you again, there is no drainage given in this particular place. So what happens now, due to that rainfall and all, water gets accumulated in this place for 2 3 days, and unfortunately this particular place doesn't face that much of sun also, that much of sunlight, so the waters are not getting that evaporate. So what happens now, slowly years and years after, the waters are were ingressing through this concrete system, and you can see here in the left side the dams you can see here. And when the dams that happened with significant corrosion, that cracks also, it is there is some you can see that cracks, how the cracks are forming. I have given some red markings. So in the entire wall you can see here, in the entire wall there is a huge crack. So very soon this concrete surface, this is actually RC wall, very soon it will suffer from that corrosion, and it's quite obvious. I am showing you the other side of this wall. See that how the damping is forming the severe cracks, and the this in the picture in the middle you can see that how the that damp has been, the wall has been that suffering from damping, and these cracks, you see that cracks in the right side you can see that how the cracks are forming in the structure. So it's very recently I took this picture. So these types of things are not good. I already informed my owner and all, but they're not taking these things seriously, and they're not doing the maintenance work properly. So in most of the cases, the in most of the apartments, you may see some types of incidents like this. You can see how significantly the wall has been corroded. So within in my opinion, within some couple of years, you will see some severe corrosion and severe delamination of concrete. So due to capillary suction of water from the other side of the roof is transporting to this side, creating a damping in the wall, followed by chlorination and carbonation. So it will happen. So this is an example I found to share. I found it quite useful and quite relatable with this topic. So I shared with you. So this is the these last two pictures. This and this one is of my own apartment where I am staying. So these are the things happening everywhere. So we should not keep the structure like this. So we'll end up with a very devastating effect. So to summarize, we have for this session, so we have seen the typical locations where that chloride attack can happen. It may happen in that marine environment or sea structures. It may happen in any of the coastal areas due to airborne chlorides, and it may happen if we use some fine aggregate which are rich in chloride content. So different types of locations. It may happen also in the different chemical plants. Different typical locations and some of the reasons also of chloride attack we have seen, and after that we have seen the mechanisms, how the reaction is happening in that concrete system when that chlorine content ingress the concrete system. If more the concentration of chloride, sorry, more the concentration of chloride, more will be the that chlorination chance of that corrosion. And we have seen later the use of bipolar corrosion inhibitors to protect corrosion, and we also saw that different various effects in the properties of concrete structure after using that bipolar corrosion inhibitors. We have seen some of the transport properties such as water sorptivity index. We have also seen that how it gives some negative impacts in the compressive strength if we doesn't follow the recommended dose, and different types of bipolar corrosion inhibitors, how it if that how it properties changes with the different types of concrete systems. All these properties we have to take care before choosing any of the materials, any of the corrosion inhibitors. So we have seen all those things. So after that we have seen some of the cracks in structural system and why it happens. Some of the case studies that why some of the cracks happened, and what happens when structural cracks comes in in any of the structures, and how they can play a vital role in corrosion initiation. After that, we have seen that how cracks can accelerate the ingress of deleterious agents such as chloride, carbon dioxide, and moisture, whatever. So if whenever you will have a cracks, through these cracks, the agents will ingress into the concrete system. So it will make a easy passage of the that for it will make easy passage for the agents to ingress into the concrete system. So as early as possible, if you see any cracks, we have to repair it to save the structure. So these types of repair will come in protection type of repair, not prevention. Using of corrosion inhibitors is coming in the prevention type of repair or in the very starting stage itself. So if you at the time of construction itself, if you take some measurements for resist corrosion, this comes under prevention corrosion methodology, prevention that mechanism. And if you once the corrosion starts, if you work on the structure for repairing the structure and to stop the corrosion, this comes under the protection of corrosion. So after that, we have seen some of the condition assessment of embedded bars, and that how to assess different types of tests we have seen, not in details but in brief. We have seen the different tests for assessment, and the need of this, also the need of non-destructive test in concrete system, we have seen. And what are the how to determine the cross section loss, and that different that hindrances in that particular the topic we have seen. After that, we seen about the preventive maintenance, why it is important, and how the things are getting neglected. So these are all the references I have used for making this presentation for you. And most prominently, I took some of the materials from the NPTEL course by Dr. Radhakrishnan G. Pillai, IIT Madras. And these are all the references, other references I have used for preparing this presentation. So at the end, I want to show you a small video of our institution. You can just see a very small video of 1 minute. So okay, so I hope so you have enjoyed this video and the session as well. So as I mentioned you earlier itself, so due to different types of technical errors and some limitation in the number of participants, we compelled to handle this session or to conduct this webinar through these recorded video sessions. So you may not get any opportunity to ask the doubts in a live session and all. So if you have any queries and any doubts, without any hesitation, you can mail us in this mail ID, or you can call us, or you can WhatsApp us. These are all the informations. So you can use this that contact for asking any types of doubts regarding this webinar, or any types of queries you have regarding this webinar, and all your queries and doubts will be answered. Don't worry, it may take some time just to post your doubts in the mail ID, or either by calling or by WhatsApping in these numbers. So all your doubts will be clarified, or will be answered to you. So we are extremely sorry for this inconvenience, for these different types of technical errors, because last time also we tried a lot, but we faced in different technical errors. A lot of the participants didn't able to join due to the limitation in the number of participants, and due to some network problem, it's quite hectic for some of the participants to listen that the content very nicely, that sound clarities, and that everything, the lot of problems comes. So we decided to conduct this webinar in recorded video sessions. I hope so you enjoyed this webinar. And at the last but not the least, I want to that give paid a very gratitude thanks to our management of Anand Institute of Higher Technology to support our Department of Civil Engineering for conducting this useful webinar. I hope so. It also that gives you some of the informations. So for any doubts or any queries, you can mail us or you can contact us. Every participant, those who registered for this webinar, will be provided by e-certificate. And for this, we need some time, because we are not going to provide you any auto-generated certificate. We are going to type and draft this certificate. So it may take some time. So kindly keep your patience and follow us for the future webinars, and you can follow us by different types of social medias. So kindly please wait for getting the certificate. Don't rush and don't lose your patience. And thank you all for registering in this webinar, and for attending this webinar, and for watching these videos from our department. I hope so it will be useful for you for your future. and you can take ideas from these steps, from these videos. And again, I am telling you, without any hesitation or without any negligency, if you have any queries or if you want to give some feedback or some suggestion, kindly please mail us in this mail ID. And you can visit our website also. There also you can find contact. And if you want to contact me directly, you can contact through this contact address. So hope so you are all are good, and wish you all the best for your future. So see you in the next webinar series. Thank you.